Okay, folks, what we got going on this week is some rotation. What we did previously with circular motion is talk about maybe a planet going around the sun or the moon going around the earth. Let's say this is the earth, here's the moon. That is circular motion, centripetal motion. That was previous. Okay, this week we're talking about rotational motion. Kind of similar, something's got to be turning, but not quite the same. A top spins, a top rotates. The earth rotates. It has an axis and it rotates around that axis every 24 hours. So we have rotational motion this week as opposed to centripetal or circular motion from last week. All right, so diving into some rotation. Before we dive into rotation, got to talk a little bit about what the units for rotation are. Well, that'll be in meters per second, right? Just like centripetal force is, right? That'll be, no, it is not going to be the same thing. No. We need to use the international unit of rotation called the radian. Now, the radian brings back bad memories from math, doesn't it? Oh, yes, it does. You're going, no, please, sir, I don't want to have any more when it comes to radians. So let me give you a little bit of a math lesson. It's quick, it's easy, and it really isn't that painful. What you do, to show what a radian is, draw a circle. Then we draw the radius. All right, R. So far, so good? Yeah, that's not too bad. Now, a radian is very simple. All it is the length. So I'm using this piece of string, the length from the center of the circle to the edge of the circle. But if I take that piece of string and lay that along the arc of the circle, like that length of the radius along the arc of the circle, that's what a radian is. So essentially, a radian is a radius. Same thing. It's just the length of the radius along the arc of the circle, but it's the same thing. So you're going to think about a radian and a radius as being the same. I mean, technically, there's a little bit difference because of where they're located, but other than that, they're the same thing. Also, what's kind of nifty cool about this angle here, get my R out of the way here, it's called angle theta. I like to call it angle Pokemon ball. Gotta catch them all. Right, but it's angle theta, if you look mathematically. And we all remember that all the way around a circle, 360 degrees. And 2 pi r is also the circumference of a circle. So let's just do a little bit of math here. 2 times pi, so I'll use 3.14. 2 times 3.14, okay, 6.28, 2 pi. Times r. Now, the r is a radian and radius, and it doesn't make any difference what the size of the circle is. The radius length is always going to be r. So what I'm going to do is take that 6.28 and divide it into 360 degrees. And if I do that, I come out with 57.3. Okay, so what's so magical about that? The magic is that this arc length, this arc length here, which is we call the radian along the outside of the circle, is always going to produce an angle of 57.3 degrees, no matter how big the circle is. Okay, if you have a little circle, a little tiny circle, you're such a little cute circle. If I were to measure that radius, lay it along the outside, take that, measure that angle, 57.3 degrees. If I have a circle as big as the state of New Hampshire, and I were to take the radius of that circle, lay it along the outside, the radian length, measure the angle, 57.3. Always 57.3 degrees is the theta value for 1 radian length along the outside of a circle. Okay. Oh, why are we going over this? Why are we going over this? For 2 reasons. One, to introduce the radian. The second reason is to come up with a little bit of phenomena that happens. Let's think about this for a second. Let's just pretend that you are on a playground of your childhood. Well, maybe not your childhood. Most of you are too young. They don't let you do anything fun anymore. But back in my day, we had these merry-go-rounds that you would push. And, looking from the top view, here's the center, you would get these things going. They would have little metal bars on the outside, and you would be able to spin this thing around as fast as you can get it going. You'd hop on, you'd have fun. You do all kinds of nifty, cool things. You could, jump off, which wasn't very smart, but you could, or you'd fall off, which just kind of happens once in a while. But let's say that you're on the outside of the circle, and the merry-go-round is cranking around like this, and you start getting a little bit dizzy. Well, two things you could do. Well, three things. One, you could stay there and throw up. Okay. Two, you could jump off. Well, okay, you could do that if you want. Or you could move toward the center of the merry-go-round. Now, you might not know physics-wise why that works, but you just kind of figure it out if you've ever played on these things before. You move toward the center, you don't get as dizzy. Well, why is that? Well, check it out. Let's say the person here, X, is moving around on the outside of our circle. And they move around yay far in 1 second, or whatever. This person here, we'll put a person here, X, is also moving with the merry-go-round. And as they turn, they are going to move, if you look at that line there, a lot less than the person on the outside. They're not moving as far, which means if you're not moving as far, there's not as much motion, you don't get as dizzy. So if you don't want to get less dizzy, move to the inside. If you want to get more dizzy, have more fun while the cool kids hang out, move to the outside. A couple things I want to point out here. One, who's moving faster? Okay, here's the question. Who is moving faster? Who be faster? Now, you might say, well, the person on the outside clearly moving faster. That's what you were just talking about. You said that you're moving faster here, so you don't want to feel as much motion. You move to the inside, right? So moving the person on the outside is moving faster. Yes and no. Yes and no, yeah. One, yes, because they are. If you were to measure how many meters this is, maybe this is, I don't know, I'm just making a number up. Maybe this is 3 meters. And they move that far in 1 second, that would be 3 meters per second. 3 meters per second. But this person here, look at that. They've only moved, well, in that scale, about 1/2 meter. Now, they're going to move that in the same time. So this person here is moving at 0.5 meters per second. Well, clearly, this person's moving faster than that person. Correct, but also incorrect. What do you mean? I don't get it. Help. Okay, well, what about in terms of radians? If the velocity is measured in terms of radians, which we know radian is a length, it's a measurement of length, okay, the length of the radius of the circle, then this person here has moved, let's say, maybe that's 1 radian. As a matter of fact, it kind of does look like it's 1 radian if I draw that along there. They moved 1 radian in 1 second. Well, so is this person. They've covered the same angle. That's the same angle as that, the same angle as that, the same angle as that. They've covered the same angle, angular motion. That's actually what we're going to be talking about. One of the terms we should be using is angular velocity. They've gone the same angle as this person out here. So this person, a person here, a person here, a person here, all these people would have covered the same angle, and therefore their angular velocity would be the same as anybody else. So who be faster? Depends what units you're using. In terms of meters per second, the person on the outside's covered more meters. Outside, move faster. But in terms of radians per second, this person, that person, or anybody on that merry-go-round would have moved the same angular distance, the same angle, and therefore the same radian velocity. So in terms of radians per second, They all move the same speed. In terms of meters per second, the person on the outside moves faster. Now we're talking about, this week, radians per second. So let's just get this mess cleaned up here for a second. And talk a little bit about that word that I use. I use angular. I use angular velocity. So there are actually two sets of words that you will see. When it comes to measuring velocity in meters per second, you will see these words. So these words are used when it comes to things going around a circle, like a satellite going around a planet. You'll see the words centripetal. Okay, centripetal velocity. You'll see the word tangential velocity or tangent velocity. Okay, those two words, which we used last week, centripetal velocity, centripetal acceleration. Centripetal acceleration is in meters per second squared. Tangent velocity, that's how fast an object is going at an instant of time when it's going around a circle. At this instant of time, an object here is going a tangent velocity in meters per second. So those are meters per second. Radians per second, you're going to need to figure out or calculate if you see the following words. I already used this one, angular. All right. So angular velocity means you have to do the units in radians per second. Okay. All right. So radians per second, angular. Also rotational. You see the word rotational velocity, that means you've got to use radians per second, because something rotating upon its axis, we talk about it going around a certain amount of angles, it's radians per second. This one also over here, there's another one that came to mind, circular. So if you see the word circular velocity or circular acceleration, that means meters per second. So we use meters per second, and we can use radians per second, depending on whether or not it's an object spinning on its own axis or an object going around another object. That's that. This is spinning on its own axis. Okay. Get rid of this. And I think we're ready to solve some problems.